Good morning everybody. Today we will try to model a given control system by use of a signal flow graph. This is another modeling technique wherein the state variables are nothing but phase variables. They are in phase variable form. Let us try to see how we can model a system, how we can arrive at the state model. If a transfer function is given and the method needs to be adopted is by signal flow graph technique. So let's take up a problem to understand this technique. So the problem says the closed loop transfer function of a system is given by Ts of S equal to S cube plus 3S by 3 upon S cube plus 2S squared plus 3S plus 1. Draw the signal flow graph and hence obtain the state model of the system. Alright. So overall transfer function is known to us. We may have to arrive at this overall transfer function in the form which can be understood from Mason's gain formula. So what exactly we mean by that and how to go about it? We will try to see step by step. So what is given in the problem is, given the transfer function, we will write T of S as, let us say, output to the input ratio, a Laplace transformed version. This is equal to S cube plus 3S plus 3 divided by S cube plus 2S square plus 3S plus 1. We will try to divide the numerator and denominator by S cube, dividing the numerator and the denominator by S cube. What do we get? We will write T of S, which we have defined as the Laplace transformation of the output function to the Laplace transformation of the input function, as this is equal to 1. This would be 3S divided by S cube would be 3 upon S square plus 3 upon S. Whole thing divided by, this would be 1 plus 2 by S plus 3 by S square plus 1 by S. It is a very simple division. So what do we do with this is, we will try to rearrange the numerator and the denominator in a specific form. We will write this as 1 divided by 3 upon S square plus 3 upon S. The denominator we will try to write it as 1 minus of minus 2 by S minus 3 by S square minus 1 by S cube. Alright. Now, if we remember the Mason's gain formula, gives the overall transfer function T of S to be equal to sigma Pk delta K divided by delta. We remember this, K equal to 1 to N, where Pk is the gain of the kth forward path. We remember this, kth forward path. And we define this delta as equal to 1 minus sum of the loop gains of all individual loops plus sum of gain product of all possible combinations of two non-touching loops minus etc. It will go on sum of gain product of all possible combinations of 3 non-touching loops and so on. It's hard to find 3 non-touching loops in any practical control system. So we will stop at this. This is how we define delta, and delta K we know is that part of delta which is not in touch with the kth forward path. Delta k is that part of delta which is not in touch with the kth forward path. Okay, so we may have to identify the forward paths, and we normally identify the loops, we normally identify their gains and then non-touching loops, etc., and we apply Mason's gain formula and get the overall gain of the system. This is something we are familiar with. Now what we do is we go back from the overall transfer function to the signal flow graph. How is that done? If you look at equation 1, we will call this equation. If you look at equation 1, the numerator suggests that it contains all the forward paths whose gains have been added. So obviously the numerator can be seen as, numerator of 1 can be seen as T of S as equal to, I will write it as there are 3 forward paths. I will write it as P1, P2, P3. There are 3 forward paths whose gains are 1, 3 by S square and 3 by S. So we identify, sorry, this is 3 by S cube. This is 3 by S cube. Alright. So P1, P2, P3 are the 3 forward paths, and the denominator is identified as 1 minus, this is written as P11, that is the sum of the first possible combination of loop gain and the second possible combination of an individual loop whose gain has been taken as P21 and P31. So we have identified the denominator in this manner, where the forward paths with gains can be written as P1 equal to 1, P2 equal to 3 by S square and P3 equal to 3 by S cube. These are the 3 forward paths. Now, as we can see, there are no non-touching loops, 2 non-touching loops, etc. 3 wouldn't arise. So these terms, that is minus 2 by S, minus 3 by S square, minus 1 by S cube, can be taken as individual loops. So because it's 1 minus of this term, if you look at delta, it is of the similar nature. So we identify P11 as minus 2 by S. This is the first individual loop whose gain is minus 2 by S. There is a second individual loop, we will write it as P21, whose gain is written as 3 by S square with a negative sign. P31, that is a third possible combination of an individual loop whose gain is 1 by S cube. So we have going in the reverse direction. Alright. So from the overall transfer function, we are able to identify the forward paths, we are able to identify the individual loops. So all the loops are touching each other. So there is no question of 2 non-touching loops. 2 non-touching loops wouldn't arise at all. So now with this background, we will construct the graph. Right? The signal flow graph. Signal flow graph is as follows. We will try to write a simple straight line. This is R of S. I'll take a unity gain. So what I get here, this is also R of S. I will try to get this first, that is P3 I will get. I'll try to take P3 and P3 we will try to simulate. Okay, so I will try to take a gain of 3 here, then I will put 1 by S, I'll put one unity and get another node, I'll put one more integrator, 1 by s. I'll put unity. I'll get another node. I'll put 1 by s. There is another node. And then I'll put unity and I'll get the variable y. I told you this is similar to the phase variable form. So in the phase variable form, the output itself is taken as the first state variable. So we'll denote this node as x1. This is x1. Alright. So this node which precedes x1 obviously would be x1 dot. So x1 dot, when pass through an integrator, you will get x1. So I will take a unity here. So what I get here is this node is x2. And here what I get here is x2 dot. This is x3. And this one more integration will give me x3 dot. These are the variables we define. However, if you look at the first forward path, this is the first forward path which has a gain of unity that has to be synthesized. So what we have synthesized now is 3 by s cube. If you travel from RFS to YFS, you will pass through 3, 1 by s, 1 by s, 1 by s. It's going to be 3 by s cube. This is one forward path we have completed. So this forward path we are able to synthesize. Sorry, this one we have synthesized. P3 we have synthesized. Alright. Now we will try to synthesize the second forward path, that is 3 by s square. So 3 by s square, so what we do is, this is 1 by s and 1 by s. So from here we will try to get 3 by s square. So what we do is, from RFS we will try to go to this node and we will take the gain of this to be 3. So what we have is 3 by s square is being synthesized as RFS into 3 and it goes to x2 dot, then 1 by s, then 1, then 1 by s and unity. So we are able to get the second forward path synthesized. The third forward path is a unity path. That means from RFS you may have to directly jump to the output, that is to x1. So this is the first forward path which has a gain of unity. Alright, so we are able to synthesize all the 3 forward paths in the form of a signal flow graph. Alright, now we may have to develop these loops, individual loops. The first loop has got a minus 2 by s. So here we will try to put a loop here. We'll try to put a loop, and the gain of this loop is minus 2. So if you look at this loop, it is x1 dot, x1 back to x1 dot. So gain is 1 by s into minus 2. So minus 2 by s. So P11 we are able to synthesize. The second individual loop has got a gain of minus 3 by s square. How do we get this? Minus 3 by s square. So this is 1 by s and 1 by s. From x2 dot till output we get 1 by s square. So from here, if we can write, it's taking as a straight line. I want it to be curved. Alright. So I'll take the gain of this to be minus 3. This now completes another loop. That is, P21 is now put in the diagram. The third loop is minus 1 by s cube. So from here, if I can take a path, this will have minus 1 by s cube. So this is the signal flow graph of the given system. Alright. So this is our x1 point, node x1. Alright. So if you can see, we have now made use of three state variables. It's a third order equation. As you can see, it's a very clear thing, because if you can look at the equation, it is s cube. So there are three state variables required. So we have defined three state variables, x1, x2, x3. We can see x1, x2, x3, and their derivatives is taken as a second state variable, that is x1 dot equal to x2. So this is, you can see, and so on. Now we will try to develop the state model. Now that we have completed with the signal flow graph, we will now try to model. How do we model? We will try to write the equations. So we will try, our state equations should be basically equations comprising of x1 dot, x2 dot, x3 dot, and on the right hand side we must have x1, x2, x3, and we may have the r part, right? So that completes the modeling. So if you look at this graph, we can easily write the signals at x1. What are the signals at x1 dot? So x1 dot, if we can see, x1 dot comprises of one signal from x2, that is x2, and one signal from x1, that is minus 2x1, and one signal from this r also, that will be from here, it will come via 1 and minus 2r. This is the equation for x1 dot. So x1 dot, this node, this input node has got signals from x1, x2 and 2r. So we will rearrange this x1 dot equal to minus 2x1 plus x2 minus 2r. This is our equation 1. Okay. Now we will try to concentrate on the other node, that is x2 dot. So node where we have x2 dot, that is this node. In this node, what are the various input signals? So one signal is here, that is x3, then you have one signal from x1, that is minus 3x1. At x2 dot, we have got minus x3 minus 3x1. Those are the two signals we have, and plus 3 times r, 3 times r and minus 3 times r. Alright, at x2 dot, we have got 4 signals, 4 input signals. One is from x3, another is from x1 via minus 3, another is r of s via 1, then it will come to via minus 3, it will come to this. So that will be minus 3r, and there will be 3r here, that is directly 3r. These are the 4 things. Now if we can group the terms, x2 dot becomes minus 3x1 plus x3 plus 0. There is no r term. Plus 3r minus 3r will get cancelled, and we get this as equation 2. Alright. Now we look at the other node, that is, we try to concentrate on the node where we have x3 dot. If we look at x3 dot, so the equation that we have at x3 dot, at this node x3 dot, we have a signal from r via 3, that is 3 times r. Alright, then we have a signal from minus r is there, that is this way it will come. This will minus 3 times r, minus 3 times r, minus x1, minus r. These are the signals that we have at x3 dot. Minus 3 times r, then minus, from here it will go minus x1, then again it will have minus r as another signal. So this can be now further simplified as equal to, further written as equal to minus x1 plus 2r. This is equation 3. Okay, if we place equations 1, 2, 3 in the matrix form, what we get is x1 dot, x2 dot, x3 dot matrix will be equal to minus 2, alright, minus 2, there's 1 x2, no x3, and then I might as well write it here. The space is little inadequate, so I may write it here. Okay, so I will write in the vector matrix form, that is x1 dot x2 dot x3 dot matrix. If you look at equation 1, we have minus 2 x1, 1 x2, no x3. The second equation, we have minus 3 x1, no x2, 1 x3, and minus x1, no x2 and no x3. This multiplied with x1, x2, x3 plus, from equation 1 we have minus 2, there is no r term in the second equation, there is 2 in the third equation. This is r. This is the state equation. Because state equation is of the form x dot equal to a into x plus b into u, where A is this matrix and B is this matrix. We are completed with the state equation. Now we need to obtain the output equation. Output equation is simple. From the Siglund flow graph, what is y of s? We can simply write what is y of s equal to. Y of s equal to, we have got one signal here. I of s is basically equal to x1. x1 into y of s. So y of s equal to x1 of s, or in time domain y equal to x1, or in the matrix form we can write this as x1 is 1, x2 is 0, x3 is 0, and the three state variables x1, x2, x3. This is our output equation. So this is another way of modeling, another modeling technique. Like it is in the phase variable form, of course, but then the method of arriving at this is slightly different. We try to make use of signal flow graph. So I suppose this example gives you an insight to state modeling using signal flow graph. So let's have a recap of this particular problem so that we will be able to understand it better before we move on to the next problem. Alright, the closed loop transfer function of a given system is s cube plus 3s plus 3 divided by this is the transfer function. Right? We have a numerator polynomial, we have a denominator polynomial. So what do? We try to manipulate the given transfer function such that it resembles the Mason's gain formula, which is given by sigma delta k pk, sigma k equal to 1 to n upon delta. This is something with which we are familiar, where pk we identify it as the gain of the kth forward path, delta, which is the determinant, is equal to 1 minus sum of the loop gains of all individual loops plus sum of gain product of all possible combinations of two non-touching loops minus sum of gain product of all possible combinations of three non-touching loops, and so on. That is how we define delta, and from delta we know how to identify delta k. We identify delta k as that part of delta which is not in touch with the kth forward path. That means delta 1, delta 2, delta 3 are identified as the part of delta which is not in touch with the first, second and third forward path respectively. Now that we have the terms like 1, 3 by s square, 3 by s cube, so we have delta 1, delta 2, delta 3 to be equal to 1, and these are that is possible when all the loops touch each other, right? So we identify the transfer function, given transfer function to be P1 plus P2 plus P3, this expression we identify, wherein we try to do one-to-one correspondence between 1 and 2, if we can call this as 2, 1 and 2 we try to draw parallels, we try to do one-to-one correspondence, okay. This is of course we were able to get after dividing the numerator and the denominator polynomial by s cube. We did this, we got equation 1, we tried to compare equation 1 and equation 2, and we were able to write the forward paths with gains as P1, P2, P3. So we are able to write this, this and this. Alright. Now from the denominator we try to identify again what is P11, what is P21, what is P31. We identify it this way. It doesn't matter which one you call as P11, which you call as P21 and which you call as P31. It hardly matters. However, one thing is clear that we have three individual loops whose gains are 2 by s, 3 by s square and 1 by s. Alright, of course with negative sign. So those are the loops. So we have to have negative feedback into individual loops. So now that we are able to identify these terms, we could draw this diagram. So we initially identified the forward path 3 by s cube. We simulated by simply taking one straight line along which we took 3 and 3 integrators we put, but thereby the resultant forward path gain was 3 by s cube. Don't concentrate on your x1, x2, x3 as of now. We simply wrote one straight line wherein we had the gain to be equal to 3. This is 1 by s, there is 1 by s, there is 1 by s. That means we put 3 integrators whose gains are 1 by s each. So the one forward path is being simulated, right? So we needed to simulate another forward path whose gain is 3 by s square. So we need to skip one integrator, right, in the path. So we skipped the initial integrator. So we took a path like this. We went on here like this. Then we went like this, right? So the path gain is 3 into 1 by s into 1 by s. Of course, you have unities here and there that hardly affects the overall gain. So it is 3 by s square. So we were able to simulate this path as well. 2 forward paths were simulated. The third forward path had a gain of unity. So it didn't have any integrator in its path. So you may have to, from RFS, you have to jump directly to the x1, which is nothing but y. Okay, output itself is the first state variable. You know, that is a phase variable method only. Alright, so we were able to simulate all the forward paths in the diagram. Now coming back to the feedback path, what was done in the feedback path? We will try to see the feedback paths. So we initially simulated minus 2 by s as one path. So we made use of this 1 by s and then we did this. This is one path, one loop, right? It starts at one node, comes back to the same node in the direction of flow of signals. So we put the gain to be minus 2 here. So the loop gain is minus 2 by s. So we were able to form one single loop. Alright. So the second loop, this is done. This is done. The second loop had a gain of minus 3 by s square. How did we simulate that? So we took two integrators in the loop, that is 1 by s, 1 by s. This loop is being taken. I may pick another color. So I'll have green only for the loops, for the entire loops. Alright. Now the second loop is like this, from x2 dot, rather this is 1 by s, another 1 by s, and we put one feedback path whose gain is minus 3. So this completed another loop. The third loop again was to have minus 1 by s cube. So what we did was, we took from this node 1 by s, 1 by s, 1 by s, this entire thing we took, right? So we put one path whose gain is minus 1. So this loop now has this transfer function. Alright. So we were able to write the signal flow graph based on the identification of these quantities. Alright. Now that we have done this much, we went on to model the system. So how do we do the modeling? If you look at the modeling equations, we were able to write this first node as x1. That is, y itself is x1. This is nothing but x of s, x1 rather. This is nothing but x1. Alright. So y equal to x1. That is simple. So the first node was treated as x1. That is tail end node, which is at the farther end towards the output. Output is for the first state variable, and the derivative of this we treated as it is x1 dot, we treated as x2. This is x1 dot, right? So x1 dot when integrated will give us x1. x1 when differentiated will give me x1 dot. So the differential will be x1 dot. x1 dot is nothing but x2. So we included a gain of unity here just to show the distinction clearly, like not to confuse. So we have x2 here, which is nothing but x1 dot. So one more integrator here would give me x2 dot, and one more integrator, this is x3 dot, x3 and x3 dot. Alright. So we were able to write the state variables in this manner. So the first state variable itself is the output, and the differential of the state variable is the second state variable x2, that is x1 dot equal to x2, then x2 dot equal to x3. So there ended our definition of state variables. Now all we have to do is obtain equations for x1 dot, x2 dot and x3 dot, right? So we needed equation for these three quantities. So how do we do? So we needed to concentrate on the node wherein we have the variable as x1 dot. So if you look at x1 dot has got signals. So I'll write it here separately only for one particular node. So we have a node here. This is a node. This is x1 dot. This x1 dot has signals from x2. This is one signal x2, and there is a signal which is coming from R. This is R with a gain of unity. We have come to x1, and from x1 it is coming up to this point with a gain of -2. Alright. I'm simply trying to make some clarity. Alright. So we have these two, and there is another signal. See, these are the possible signals we have at x2 dot. At x2 dot, this is the node x2 dot. At x2 dot, we have a signal x2. This signal x2, and there is a signal from x1 with a gain of -2, and there is a signal from R via unity via x1 via -x2. So these are the three possible signals which are meeting at x1 dot, right? So we are able to write this equation. Now we go on to the node x2 dot. So x2 dot again has got x2 dot has got three signals. That is x3, x2 dot has got signals like x3, so should we write that also? We'll try to see. This is x3. We have a unity path here, and this is x3 dot. Okay, this is one signal. Then there is this x1. So we have minus 3x1. Okay, and then there is a signal this way. From R, we have one signal like this directly via 3 times R, and there is another signal which is meeting at x1 via R. This is also R into 1. So if you look at this combination, what is x3 dot equal to? If we write x3 dot equal to, this is x2 dot, this is x2 dot. x2 dot equal to three different signals we have. That is one signal from x3, another signal from minus 3x1, 3 into x1, and then plus 3r, this one, and then minus 3r from here till here. This is minus 3r. So we'll get this equation. Okay. The third equation we again obtain from x3 dot. So we identify the node x3 dot, that is this node x3 dot, possible signals. So we have one signal here, this is 3, this is r. So what we have here is x3 dot is equal to one signal from this one, another signal from x1, this is x1, and the gain of this is minus 1, and then there is one r which is coming here, that is from r there is a signal. So we have 3 signals at x3 dot. At x3 dot we have 3 times r minus x1 and then minus r. So this will come to this much. So we need to do this much, and this would be the state equation. That is something we are so familiar with, of transforming the given equations to matrix form. So we get the state equation in the output equation. This completes the modeling using the signal flow graph technique. All right, we can stop here.